Welcome to this lecture. So in this class, we'll see about a new type of process. Uh, In We have discussed earlier that a first order system arises because of the presence of capacitance and resistance. That is both capacitance and resistance together. If I have a system having which has both capacitance as well as resistance, that leads to a first order lag. But there are certain systems which have only capacitance, pure capacitance. So there are certain systems which have only capacitance. There are systems with only capacitance and no resistance. There are systems which have only capacitance, pure capacitance, but no resistance. So we'll see about such a system having only capacitance, or it's also known as pure capacitance, and no resistance. Such a system will have a transfer function of the form K by S. So unlike first order system, which has got both C capacitance and resistance, having a transfer function K by tau S plus 1. But this system, pure capacitance process, will have a transfer function of the form K by S. So one such example is a tank with a constant outflow. So tank we have been seeing, we have seen earlier on a couple of occasions and couple of lectures. So you have a tank where the liquid is flowing through the tank, but outlet here is constant. The outlet is maintained by a pump which can maintain a constant outflow, the constant outflow pump. So the outflow Q naught is constant, whether there is a disturbance in Q or no disturbance, steady state, unsteady state, whatever is the condition, Q naught is constant. The outflow is constant. So if the outflow is not constant, if the outflow is a function of H, if the outflow depends on H, then it becomes a first order lag. It will have both resistance and capacitance. But in this case, the outflow is constant. There is no resistance here. Okay, there is no resistance. The resistance is overcome by the pump. That's why no resistance. So resistance is overcome by the pump. The pump maintains a constant outflow. So let's see what is the transfer function of this. So the usual notations: Q is inlet volumetric flow rate, Q naught is outlet flow rate, that is constant. A, area of cross section, rho, density of the liquid, both we select to be constant. We assume that both area is uniform and constant. Area is uniform, area of the tank uniform and constant. Density of the liquid is also constant. H is the height, and Q naught, I said Q naught is constant outflow. Now if you write the material balance, steady state mass balance, unsteady state mass balance. This unsteady state mass balance, as I had done in my earlier lecture PC48. You can refer to this equation. You can refer to this for this equation. The unsteady state mass balance, it gives Q equal to Q naught plus A dH by dt. This you can refer to this lecture PC48 title PC48 in my video series. So at steady state, Qs equal to still Q naught, because Q naught is constant. Remember, you are not using Q naught S here. Q naught is constant, same at steady state as well as unsteady state. The outflow is same Q naught. Outflow is constant because of this pump which maintains a constant outflow. So on steady state equation is Qs equal to Q naught, subtract 1 minus 2. This will give you Q minus Q naught equal to A dH by dt. And A dH by dt, I will write it as d capital H by dt, where capital H is the deviation variable, H minus Hs. Hs is constant. So this dH as well as this dH are equal because Hs is a constant. And Q minus Q is again deviation variable, Q equal to A dH by dt. So you have a differential equation and take Laplace transform, you get this. And simply, and H naught is what? H naught is initial deviation. Capital H naught is H evaluated at t equal to 0. At t equal to 0, H equal to Hs. So the initial deviation H naught is 0. This is 0. H naught is 0. So remaining terms gives you this. Hs by Qs equal to 1 by As. So this is the form K by S. What I said, K by S. K by S. K is 1 by A here. So this is the transfer function of this system, this liquid tank with a constant outflow. So if you have a tank with constant outflow, this is the transfer function. If the outflow is not constant, if the outflow is a function of the head as well and resistance, then it has led to first order lag, first order transfer function as we have discussed in PC48. Now this outlet pump maintaining a constant flow rate, whatever be the head, whatever be the flow rate, this Q naught is constant. The resistance is overcome by the pump. So there is no resistance here, only capacitance. So you have the transfer function is this way, 1 by AS. Now let us see how this responds to some disturbances. So let us consider a unit step input, okay? So this is simple, Q of t equal to UT, step input, unit step input. This is a unit step input. So when you give a unit step input, what happens to the height? So this is a usual procedure to find ht from qt. How do you find ht? Usual procedure, take qs, take Laplace transform. Q of s is 1 by s. Substitute here, h of s equal to 1 by a square. If you substitute qs into this, h of s equal to 1 by a square, and take L inverse Laplace, you get h of t equal to 1 by a t, or h minus h equal to hs plus 1 by a into t. So what is this sort of what type of function is this? This is a ramp function, right? This is a ramp function, continuous or linear function. It continuously increases with time. You give a step input. Step input is what? Step input is bounded, right? Step input is bounded. So I give a step input. This is step input. Q of t equal to u of t. This. But what is the response I get? So response is continuous ramp function. So a change in inlet flow causes the height to increase without limit. So a small change, small increase in the inlet flow, what happens to the height? Height changes like this by a ramp function. So the tank will overflow after some time. So a small change in Q, small increase in Q can make the tank overflow. The same way, reverse, a small decrease in Q can empty the tank at some time and the pump will run dry. There's a risk of pump running dry. So that is the characteristics of this process. So there's a continuous increase ramp input. The height is changing by a ramp input when you give a small, when you give a bounded input. In step input is a bounded input, but the response grows unbounded. This is a system with no self-regulation. No self-regulation. Because there's no self-regulation, it continuously grows, unlike first order system. Or it's also known as a pure integrator process because it behaves as if there is an integrator between its input and output, between Q and H. So it's known as a system is known as a system with no self-regulation or pure integrator process or systems with no resistance, system with no resistance or system with pure capacitance. So all these things indicate this process only. And they'll have transfer function of the form K by S. This particular example has a transfer function 1 by AS. So such a process can cause serious problems in control system because a small change will make the output behave like this and the system cannot balance itself. It cannot balance itself. It will result if the change in Q is increase, it will result in overflow. If the change in Q is decrease, it may cause the pump to run dry. It may cause running an empty tank. This attribute only is called no self-regulation. No self-regulation. Examples are commonly encountered. Such examples will commonly occur in industrial chemical processes like tanks with liquids, vessels filled with gases, storage tanks with continuous flow. of raw materials, finished products, etc. So in such cases, this type of lag, pure capacitance, or no resistance, or no self-regulation type can occur. So a tank with a liquid outflow, simple liquid inflow and outflow, can be of different types. It can be first order, having both capacitance and resistance. In that itself, there are a couple of differences, couple of different cases, like linear tank, non-linear. And in this case, this is a tank with constant outflow, resulting in only capacitance, pure capacitance. I hope this is understood. If you have any questions, please leave them in the comment section. See you.